Well, hello everyone. So today in this video, we're going to be talking about Newton's law of universal gravitation. Okay, so here we go. Universal gravitation. The gravitational force between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Kind of a mouthful. All right, so we're going to kind of condense all of this into one relatively simple equation. All right. F sub g equals big G m1 m2 all over r squared. And here we go. This represents that entire wordy equation, right? The force of gravitation is proportional to the product of the masses of the two objects and inversely proportional to the square of the distance between their centers. Okay, so what I'm going to do is I'm going to go through each symbol and kind of talk about them a little bit. To start, let's go with the masses. Okay, you know what mass is? It's the measure of how much stuff it is, measured in kilograms. Nothing too groundbreaking there. Your force of gravity, right? Previously, you may have referred to this as the weight of an object. It still can be used in that way, but this equation is generally more for objects that are far away from each other, like from the Earth to the moon or the Earth to the sun, stuff like that. Okay, we'll see in another video how we can apply this to other scenarios, but for now we're just going to stick with this. Okay, F sub g, your force, your masses, cool. This r is not radius. Okay, this r is the distance between centers. Okay, so a common mistake that people make is they see this r, oh, that means radius, so then, oh, let me take the number they give and divide it by 2. No. Okay, yes, we kind of travel in a circle, right? So the distance between the centers is already the radius. Right? So you don't need to cut that value into it. This is just the distance between their centers. Now, I'm really emphasizing the distance between the centers part, because if they tell you that the distance between the surface of planet X and a moon is, you know, blah, 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 but they tell you it's the surface of planet X, you have to take into account the radius of planet X as well. But you'll get to that in a given problem on another day. Anywho, we'll talk about this over r squared in a bit. What I want to kind of focus on right here, right now, is this g. Okay, so I'm going to erase the equation. Okay, this g is a constant. It's called the universal gravitational constant. Universal gravitational constant. Okay, and its value is 6.67 times 10 to the negative 11 Newton meter squared per kilograms squared. Okay, again, kind of a mouthful, but this value is one of the most important values in all of physics. It shows up in Einstein's work, it shows up in Newton's work, shows up all over the place when dealing with cosmology, or especially astronomy, things like that. Astronomers use this value all the time. Okay, so this is what we've got, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. It's important that you understand that this must be a capital G. Capital G represents this value. Lowercase g represents the acceleration due to gravity near the surface of a planet or a moon or a star or something like that. Okay? Make sure you keep those two things separate. Now, what I want to talk about moving on is this 1 over r squared. Now, this 1 over r squared represents the inverse square law. Basically, what it means is as the distance increases, the force will decrease by the square of the change in distance. Likewise, when the distance decreases, the force will increase by the square of the change. So let's see what that looks like. I'm going to make a little chart. Okay, we're going to say that over here is our distance. Over here is our force. Okay. Now, I'm going to give us a baseline. Let's say if our distance is r, we'll have a force of value F. Right, now, what happens if I have a distance of 2r? Well, basically what happens is I'll have 1 over 2r squared, which becomes 4r squared. So basically you get this 2 turning into a 4, and you get F over 4. Okay, so the distance doubled, but the force was cut to a quarter of what it once was, because 2 squared is 4. The distance got bigger, the force got smaller. On the flip side, let's say you cut the distance to a third, so you have r over 3. Well, if you have r over 3 all squared, you end up with 9 over r squared, because 3 squared is 9. So what you'll end up with is 9 times your force. Right? The distance got smaller, the force got bigger. 3 squared is 9. That's the inverse square law. Okay? That is very, very important for this equation. Okay? Just like any force, the force of gravity is measured in newtons, and we kind of know how to work with those. Okay? So that's all I've got for this particular video. In another video, we'll go through applications of that equation. How can we calculate the acceleration due to gravity on maybe some distant planet if we only know a couple things about it? How can we calculate the orbital speed of a given orbiting object? How can we calculate the orbital period of those things? So that'll be in another video. But for now, that's all I got there. I'll see you next time.